Okay, let's get started. Now in this next video, this is part 2. We've already looked at determining limits from data by using tables to determine the limit of a function. Now what we're going to look at now is determining limits from graphs. So what if you don't actually have the function, but you have the graph? How would you go about determining the limit of that particular function? So that's what we're going to be looking at in our next video here. So let's go ahead and get started with our first function. I'm going to give you the function on this one. Once again, make sure you have your graphing calculator there with you. Make sure you have it turned on, because I'm going to ask you to graph some of these. Some of them I'll have graphed already. So to get us started, take a look at this first function. It says f of x equals 1 for x equal 2. Right? And except, or x not equal to 2, except at 0, where x is equal to 2. So with this particular, this function here, I'm going to do the limit as x approaches 2 of f of x equals 1 for x is not equal to 2. And at 0, x equal 2, the graph drops down to 0. So what you're talking about when you look at this type of function, okay, this is simply the function f of x equals 1, or y equals 1. Now the graph y equals 1 is a horizontal line crossing the y-axis at 1. So, except at x equal 2, where you have it drops down, right? So let's take a look at the graph real quick. So I'll give you a little sketch here. So just a quick sketch on PowerPoint. Right, so 1, 2. So we're going to graph f of x equals 1, which is just a horizontal line. Right? So you can see, except at x equal 2, the function drops down to 0. Right? So x is 0. Right? So the y value will be 0. So as you look at this graph, so determining the limit by looking at the graph here now, here's what we want to do. Looking at the graph coming from the left-hand side and the right-hand side. The first thing you're going to notice about this graph is there's a hole in the graph. Right? Now, the graph doesn't matter now, the hole doesn't matter. So as you look at the function, we're going to find the limit as x approaches 2. So here's 2. Now remember, we're going to consider, as you look at the graph, we're going to consider from the left-hand direction and the right-hand direction. Now, as you look at this hole, okay, the hole really doesn't matter when we're determining the limit. It does, but keep in mind we're finding the limit as x approaches 2. So remember, we never actually get to 2. We just get closer and closer to 2. If you did get all the way to 2, it would drop down to 0. But remember, we just get closer and closer to 2. All right, so coming from the left-hand direction, as x approaches 2 from the left-hand direction, y is always 1. So we get our corresponding y value. So from the left-hand direction, as x approaches 2, y is 1, always. Now remember, we never actually get to the hole. We just get closer and closer to the hole. Now coming from the right-hand direction, as we approach x from the right-hand direction here, we approach 2, we get closer and closer to 2 from the right-hand direction. Well, from the right-hand direction, y is always 1. Right? So approaching from the left-hand direction, y is always 1. Approaching from the right-hand direction, y is always 1. So remember, we don't actually get to the hole from either the left-hand side or the right-hand side. And this is really confusing for a lot of students, because they'll see that hole and they'll see it drop down, and a lot of students will think that the limit should be 0. It's not, because remember, we never actually get to 2. So as x approaches 2 from the right-hand direction, y is 1 everywhere. As x approaches 2 from the right-hand direction, y is 1 everywhere. So we say the limit of this particular function at 2, right, at x equal 2, as x approaches 2, is 1. Okay, not 0, because remember, we never actually get to the hole, we just get closer and closer. We approach 2 from the left-hand side and the right-hand side. So as x approaches 2, f of x approaches 1. From the left-hand side and the right-hand side, we never actually get to the hole. So we say the fact that f of 2 is equal to 0 has no bearing on the existence or value of the limit as x approaches 2. So the limit in this particular function should be 1. Okay, let's take a look at our next function. I'm going to go ahead and give us the function here first. Okay, we're going to try an absolute value function. Now, you got to kind of watch out. Some of these graphs can be kind of odd. So let's start off with the first one. Now, if you would, take you a second or two, hit y equals on your graphing calculator, go ahead and type in your function, so the absolute value of x over x. And what we're going to do here, we're going to find the limit as f of x, absolute value of x over x approaches 0 this time. So if you would, go ahead and put that in your function list, hit graph, and we need to zoom it in. So we need to do zoom it in a little bit so you can get a better look at it. But after you graphed it, let's see if your graph should look something like mine here. So I kind of did a little sketch of what the graph should look like. And it looks something like this. So here's my coordinate plane. And you get this type of graph right here. So just looking at the graph now, determining what our limit should be if we have one. Right? So now remember, now you've got to consider the graph coming from the left-hand direction and the right-hand direction. So let's come from the right-hand direction first. So we're going to find the limit as x approaches 0 from the right-hand direction. Now, from 0 to the right, all values greater than 0 here on the x-axis, you can see is 1. So coming from the right-hand direction, okay, the corresponding y value would be 1. Now, as x approaches 0 from the left-hand direction, okay, your corresponding y values are all negative 1. So what you're looking at here, the right-hand limit is 1, the left-hand limit is negative 1, and you get, they don't meet. So what that indicates is that there is no limit in this particular function. So as you look at it, so the right-hand limit of f of x is equal to 1 as x approaches 0. So coming from the right-hand direction, your limit is positive 1. So coming from the left-hand direction, the left-hand limit as x approaches 0 is negative 1. Now, anytime the left-hand limit and the right-hand limit are different, then the limit doesn't exist. So what you've got the graph will have a jump in it, or a gap. There'll be a gap or a jump in your graph. So since the left-hand limit is not equal to the right-hand limit, the limit as x approaches 0 does not exist. So you get that jump or gap in your graph. Right? So that indicates that the left-hand limit and the right-hand limits are different. Right? So there's simply no limit. Now there are limits at other values of x, but not at x equals 0. Okay, let's move on. Now once again, if you would, hit y equals on your graph and go in your calculator, and let's see if you can graph the function 1 over x squared. So go ahead and put that in your calculator. Take a look at the graph. Now I already have just a quick sketch on the PowerPoint here of what the graph will look like. So you get something like this right here. Right, so something like this. Now once again, we're going to use the graph to come up with our limit. Right, now notice what happens. Now we're going to find the limit as x approaches 0 of 1 over x squared. So this is generally what the graph is going to look like. Now, let's take a look at the left-hand limit first. So coming from the left-hand direction, as x approaches 0, notice what happens to the y value. Now, the y value gets bigger, bigger, bigger. So basically, y goes to infinity. So what we have here, 0 is a vertical asymptote. So as x gets closer and closer to 0, y gets bigger and bigger and bigger. So basically, y goes to infinity as x gets closer and closer to x. Infinity is not a limit. So same thing from the right-hand direction. As x approaches y from the right-hand direction, the y value approaches infinity. So once again, infinity is not a limit. So we say that the limit as x approaches 0 of this particular function does not exist. So as x approaches 0 from either the left or the right, y approaches infinity. So that indicates that the limit doesn't exist. So if you got a vertical asymptote, holes we can remove a hole. So holes we still have a limit, but a vertical asymptote you can't get rid of them. You can't get rid of a vertical asymptote. They're there, and there's no limit. That means when we get into taking derivatives later, you won't have a derivative at x equals 0 either. So the graph isn't continuous. So in this case, there would be no derivative either. So let's get started with the next one. One more here I want you to do with your calculator, then we're going to try a couple that are already graphed for us. So if you would, hit y equals on your calculator again, type in sine of 1 over x, and take a look at your graph. So go ahead and put that in your calculator. Now what we're going to do is we're going to find the limit of, as x approaches 0, of sine 1 over x. So we're going to put it in your function list, take a look at the graph. Now also what I want you to do with this function before we bring it up here, I want you to zoom in on the function 2 times. So do zoom, then to zooming in. So zoom in it twice, and what you should get is this right here. So the graph is oscillating back and forth. And you can see that on a chart, a little chart that I developed here. So once again, we're looking for the limit of sine 1 over x as x approaches 0. And I tried several values. The first one I tried in sine 1 over x was 2 over pi. And I just used pi for pi. So 2 over pi is positive 1. Well, 2 over 3 pi is negative 1. 2 over 5 pi, positive 1. 2 over 7 pi, negative 1. And you see the pattern. So what happens in this particular graph, it oscillates back and forth. It jumps back and forth from negative 1 to positive 1. So what you get is this right here, coming from the left and the right, like here. So it oscillates back and forth. Oscillating behavior indicates no limit. So this particular function here, and you see this basically with some trig functions you may have oscillating behavior. So this here would not be, does not have any limit either. So f of x oscillates between 1 and negative 1. So we keep doing this right here, back and forth. It indicates no limit. So the limit does not exist here. So it does not exist. So let's try this one here. Now I'm going to do this. We're going to do this first one together. Now the second graph I want to get you guys to do first. I'm going to ask you to pause it and have you guys see if you can do each of these here a little bit one at a time. So let's start off with the first one. Now this time I'll give us just a graph. Right, so take a look at it. Right, now here's our graph. You can see it's several parts. You got an asymptote in here. So let's try our first limit. Now just looking at the graph. So let's see if we can determine what the limit of g of x as x approaches 1 will be. So what will be the limit as x approaches 1? Now, looking at the graph, it's kind of hard to see maybe on your video, but this is, so come over here, this is 1, 2, 3, 4, all the way down to 8. Now 1 is right here. So as I determine the limit from my graph, as you come on up to the graph, notice there's no hole, there's no jump or gap, there's no asymptote. So the limit from the graph here should be simply the corresponding y value. So follow the graph all the way up, come over to y should be 4. So once again, this is 1, all the way up, over, that's your limit. So it's going to be simply the corresponding y value. So we said the limit as x approaches 1 should be 4. Okay, let's try another value. Let's try the limit as x approaches 2.5. 2.5 would be, this is 1, 2, 2.5 would be right here. So once again, I notice as you come up to the graph, there's no hole, no jumps, no gaps. So we want to simply follow the graph all the way over to its corresponding y value, which would be 0.5. So when x is 2.5, y should be 0.5. So we say that the limit as x approaches 2.5 should be 0.5. So like this right here, so 0.5. Okay, let's try another value off our graph now. Let's try the limit as x approaches 2. So let's try 2. So this is 1, 2. Now coming up to the graph, you'll notice you can see the jump or the gap in the graph. Now that indicates that the left-hand limit and the right-hand limits are different. So there is no limit at x equals 2. Right? So you can see that the left-hand limit would be 3. The right-hand limit would be 2.5. So the left-hand limit is 3. The right-hand limit is 2.5. So the left-hand limit and the right-hand limits are different. So this particular, as x approaches 2, the limit doesn't exist. So we say the limit here does not exist. Let's try another one. Let's try the limit as x approaches 3. Now you can see 3, you can see that vertical asymptote, right? And once again, this is an asymptote. You can't get rid of it. There's nothing you can do to it. Coming from the left-hand direction, the left-hand limit, y goes to infinity. From the right-hand direction, as x approaches 3 from the right-hand direction, y approaches infinity. So in this particular instance with the vertical asymptote, there is no limit again. So the limit as x approaches 3 does not exist. So this one does not exist. But if you have any type of vertical asymptote, you're not only is the graph not continuous, there's no limit either. All right, so here's just a couple examples off this particular graph. Let's try the next one. And after each one, I'm going to pause for about 5 to 10 seconds, and I'm going to let you all write your answer down first. And let's see what you were. Let's see if you get the correct answer on the next one. Now, the next one has even more jumps and graphs and gaps and asymptotes on it. Let's take a look at this one. Now, so here's our graph. And there we go. Now you can see they got several values here. Let's start off with the first one. I'm gonna pause for about 10 seconds, and I'll let you write the answer down first. Now, as you look at this, as you look at the graph, this is their y-axis. This will be 1, 2, 3, 4. And then to the left will be -1, -2, -3, -4. So it may be kind of difficult to see on your computer or whatever, but I'm going to indicate they're not real big on the graph that I put on the PowerPoint. So let's start off with our first value. I want to bring it up, and I want to pause for 10 seconds or so. I want to let you guys think about it. Write down what you think the answer should be. So what should be the limit from the graph? I'm going to kind of step out of the way a little bit, about 10 seconds. But write down what you think the answer should be, and then we'll come in and we'll take a look at what the answer should be. So here goes. Let's do the limit as x approaches 1. So what do you think? What do you think the limit as x approaches 1? One is right here. Now, so take a look at it. And I want to pause about 10 seconds. I'm going to let you write down what you think the answer should be. Okay, everybody, even I can see the left-hand limit and the right-hand limits are different. Okay, you get that jump in your graph, right? So there's the limit at 1 does not exist. The left-hand limit is +1. The right-hand limit is -1, so there's no limit here. So the limit here doesn't exist. I'm going to try the next one. Now I'm going to bring the problem up. And once again, I'm going to pause about 10 seconds. I want you to think about it. Write down what you think the correct answer should be. And here it goes. So let's try this here. This would be the limit as x approaches 2. Now 2 is right here. So see if you can follow the graph. Let's see if you can determine what the correct limit should be here. All right, let's see what you got. Now looking at 2, coming up to the graph, you notice now there's no jumps, no gaps, no asymptotes, so the limit should simply be the corresponding y value. So come straight up to your graph, over to the y-axis, the limit is 1. All right, so the limit is 1. So let's try this. So you can see we've got the answer there on our PowerPoint. Let's try the next one. Now this time, instead of me pausing, I want you to pause the video. Write down your answer, what you think it should be, and then whenever you come back, we'll go ahead and go with the correct answer. So I'm going to pause again. Let's see what you get with this next limit here. We're going to do the limit as x approaches -3. So -3 is right here. So take a look at it. Let's see if you can determine what the limit should be. So I want you to pause the video for a few seconds, and start it back, and then you can check your answer on this one right here. Okay, so you're welcome back. So hopefully you've already written your answer down. And as you look at this, as you look at the graph at x equals at -3, you'll notice you can see the gap or the jump in the graph. Okay, that indicates the limit doesn't exist. The left-hand limit and the right-hand limits would be different. So the correct answer here does not exist. Okay, let's try another one. Okay, let's take the limit as x approaches -1. So -1 is right here. Now once again, pause the graph, pause the video for a few seconds until you can determine the correct answer, and then write it down. When you come back, we'll go with the correct answer. Okay. Now, I'm assuming that you've already got it paused, you already have your answer down. So as you look at this, you notice the graph, there's a vertical asymptote. So that indicates coming from the left-hand direction or the right-hand direction, the graph goes to negative, the y value would go to -infinity. So this indicates that there's no limit here. So the limit as x approaches -1 on our graph doesn't exist. So there's no limit here. Okay, let's try the limit as x approaches 3. Now, this is 1, 2, 3 is right here. Let's see if we can get this one correct. Now, once again, I want you to pause the video, write down what you think your answer should be. So look at the graph, look at the graph. And when you come back, we're going to let you kind of check your answer and see how you were able see how if you were able to get the correct answer on this one. Okay, I'm assuming that you've written down the answer already. So you've thought about it. Now, as you look at this particular, at the graph at x equals 3, come on, wow, this one has a hole in it. Now, keep in mind that holes, we say holes can be removed. So you notice as you come in from the left-hand direction, as x approaches 3, remember, we never actually get to 3, so the hole really doesn't factor into our answer. As x approaches 3, the y value approaches 3 also. Coming from the right-hand direction, as x approaches 3, the y value also approaches 3. Now keep in mind, if we ever actually got to 3, okay, the function would jump up to 4. But the limit from the left-hand direction and the right-hand direction is 3, not 4. So we say the limit as x approaches 3, is 3. Okay, the fact that there's a hole doesn't matter. Right? Now the graph is not continuous, that's okay. Now we'll see later that algebraically anyways, we can remove holes. Right? But then from the graph here, the hole really doesn't matter. Now this is the type of problem, type of question you see on the AP Calculus exam, and it's missed by a lot of students too. So a lot of students, when they're looking at this particular limit, they'll estimate the limit as 4, and it's not. So keep in mind, from the left-hand direction, you never actually get to 3. So the number that y approaches is 3, not 4. And then from the right-hand direction, you never actually get to 3. And the value that y approaches is going to be 4. So it's going to be 3 also. So we say the limit as x approaches 3 should be 3 at x equals 3. All right, now now next we'll take a look at some common behavior associated with the non-existence of a limit. Now we looked at a couple of these at the beginning of this video. So here's a couple instances in which a graph or a function will not have a limit. So here's the first one. Anytime the left-hand limit and the right-hand limits are not equal. So anytime the left-hand limit and the right-hand limits are not equal. So if the left-hand limits and the right-hand limit, that indicates a jump or a gap in your graph, the limit doesn't exist. Right? So that's the first thing I want you to remember. The left-hand limit and the right-hand limits have to be equal to each other. So the graphs would have to meet. Right? Now, the second behavior associated with the non-existence of a limit. This is an instance in which the limit won't exist. So this is when f of x increases or decreases without bound as x approaches some number. So as x approaches c. So this, now what they're talking about here in part 2 typically is an asymptote. So if you have an asymptote, so x approaches some number, the y value goes to infinity or negative infinity. So this is unbounded behavior. So there's no limit. So if you have a vertical asymptote, there's no limit. And you can't do anything about an asymptote. You can't get rid of it. It's not like a hole. Holes can be removed. Or they say in calculus, we can fill the hole. Right? But now, an asymptote, you can't. It's there. We're stuck with it. There's no limit. Now, the third behavior associated with the non-existence of a limit is oscillating behavior. So f of x oscillates between two fixed points as x approaches c. So anytime you have oscillating behavior, remember, the graph is doing this right here. The one we looked at earlier was sine 1 over x as x approaches 0. So you get that oscillating behavior. You would see this typically with maybe some trig functions. All right? So anytime you have oscillating behavior, there's no limit. So just to review, left-hand limit does not equal the right-hand limit. That indicates a jump or a gap in your graph. A vertical asymptote, so f of x, so y increases or decreases without bound, right? So a vertical asymptote, and last, oscillating behavior. So that's three instances in which you would not have a limit. And that's the end of our video.